Hello and welcome to Tattva Conversations and Explorations. For our second episode on physics, we sat down with Professor Chad Orzel. Professor Orzel is a professor at Union College in Schenectady, New York. He has a BA in physics from Williams College and a Ph.D. in chemical physics from the University of Maryland, College Park. He has been blogging about science since 2002 on his own site at scienceblogs.com, at Forbes, and on Substack. In 2021, he was named a Fellow of the American Physical Society for his work on public communication of science. He's also the author of 5 books explaining science for non-scientists: How to Teach Quantum Physics to Your Dog, and How to Teach Relativity to Your Dog, Eureka, Discovering Your Inner Scientist, Breakfast with Einstein, The Exotic Physics of an Ordinary Morning, and his latest, A Brief History of Timekeeping. In this interview, Professor Orzel talks about what physics is fundamentally and also discusses its goal. He shares what excites him about physics and how he endeavors to bring the same excitement to his students. He also talked about some of the biggest questions physics has asked, the amazing world of quantum mechanics, the mystery of the meaning of time, and the role that imagination and intuition play in developing physics. He too shared his take on Stanley Kubrick's film 2001: A Space Odyssey and what he believes the monolith stands for. We hope this conversation can help the listeners see the tattva, or the true essence of physics, and the important role it plays in helping us understand the world we live in and appreciate the fundamental forces that lie underneath everything. Hello, Professor Orzel. Welcome to Tattva.
Thank you for having me on.
We are very, very happy to have you, and thank you for your time that you've agreed to give us. So I'd like to start with a very basic, a very fundamental question. What is physics?
So I would say that physics is the study of sort of the most basic interactions in the universe, which, if you really break things down to the sort of fundamental particle level, there are 4 ways that particles in the world interact with each other. Those are electromagnetism, gravity, and then the strong and weak nuclear interactions, right? And that's what holds all of matter together. You know, the strong and weak, the strong interaction holds the nuclei of atoms together. The weak plays some role in that. The electromagnetism holds atoms together, holds the electrons into the atoms and binds atoms into molecules and all larger structures. And then gravity is responsible for, holding large, planet scale kind of objects together, so pulling things in. So those are the 4 interactions, and then that's a very simple seeming system, but the consequences of that sort of spiral out, and you get this increasing complexity as you go out. But fundamentally, physics is about taking relatively simple systems with just those handful of interactions, and then looking at how everything plays out. And that covers a lot of scales, and sometimes we take sort of higher level abstractions of things we'll talk about. There's physics of materials, where you're not talking about individual atoms, and worrying about the electromagnetic interactions between them, but you think about something like, a big pile of granular material, but that's acted on by gravity, and there are forces between the grains in that are still, it's a relatively simple system with, only a few moving parts, but that gets you a lot of complexity in the end. This is sort of the distinction between physics and other sciences, is largely a matter of where you make your sort of what level of abstraction you work at, right? So we talk about atoms and the internal structure of atoms a lot in physics. In chemistry, they tend to talk about groups of atoms, right? You group them together into molecules, and then those molecules interact with each other at kind of a one step up the ladder of abstraction. You talk about biology, then you're talking about, large groups of molecules that aggregate together to make cells and pieces of cells, and, lots of cells that aggregate to make organisms, and so on up the chain. So,
wow.
So that's sort of the difference. So.
That's amazing. That's, of course, I had no idea that, or at least I could not see this panning out, that essentially these four forces seem to
Mhm.
make up the skeleton of all the subjects that we study. And depending on the degree of abstraction, if you could explain that, determines whether we're studying physics, biology, chemistry. Is that right?
Yeah, I mean, so this is a joke. In academic science, physicists sometimes have a reputation for being like exceedingly arrogant, just declaring that everything else is really physics secretly, but really it is. The only people who have one over on us are the mathematicians, who say that really physics is just sort of dirty math. But the idea is, we've got this handful of particles that interact with these four interactions, and if you think about that, that pulls quarks together to make protons and neutrons, pulls protons and neutrons together to make the nucleus of an atom. Then you pull in electrons that make whole atoms, and then you can keep doing this. You can talk about everything in principle, starting with, well, there are 6 kinds of quarks and these interactions between them, and go all the way up the ladder. But as you start to get anything even more complicated than a hydrogen atom, right, that's not really a useful way to look at it, because you have just so much complexity in all of the little pieces that have to be there. So what you do is you start to make abstractions. We think about a proton not as a collection of quarks that are bound together by the strong force, but it's a particle in its own right that has a positive charge and a particular mass, and that's it. And we don't worry about the substructure of that very much. And then you can talk about the physics of atoms as, I've got protons that are one kind of particle, I've got neutrons that are another kind of particle. Those are in the nucleus, and then that determines some properties there. And then we worry about the electrons on the outside. And so what you're thinking about, the levels of abstraction are sort of, what are you thinking about as discrete objects whose substructure we're not going to worry about? So we've got, protons and neutrons. You can think about just protons and neutrons and do a lot of nuclear physics and never worry about them splitting apart into quarks and making exotic kinds of particles and that sort of thing. Or, you could do atomic physics, where you think about the nucleus it has some mass, it has a positive charge. And then we're really worried about the electrons around the outside and how they behave.
Right.
And that's another layer of abstraction. If you talk about molecular physics, frequently you're thinking about the atoms as discrete entities that, like, we're not really worrying about the substructure of those. We're thinking about, how do 2 of them interact? Right. And that's sort of the kind of abstraction that I mean. So, it's just too complicated to talk about all the thousands upon thousands of particles that are involved if you're dealing with the most fundamental level. So we chunk them together into bigger things and agree not to talk about the substructure of those bigger things.
Okay. I think I get a sense of what you're saying. You're also saying that there are so many things to study about, and then you kind of have to filter out what best can be studied without worrying about what other things affect it. So yes,
you're picking some subset of all of the infinite variety of things that we have in the universe, where you're focusing in on some subset of it. And in order to do that, you have to say, well, look, there's stuff that's more fundamental than the pieces I'm talking about,
right?
But I'm not going to worry about that, right? We're just going to take as a given. I guess another way to think about it would be, if you think about like biology, something would be like a little more everyday, right? We know that people are made up of cells, right? But most of the time you don't think about, people as cells. You think about a person as a unit. Right. They are a whole individual, and we're going to worry about the behavior of people and groups of people. And, it's only in certain odd situations, where mostly medical contexts, that you have to say, okay, thinking about this person as a complete unit isn't working anymore. We need to look at some problem that's at a more fundamental level, and then you start to think about organs or tissues, or all the way down to the level of individual cells.
Yeah, so
it's the same sort of thing, just
right.
Yeah,
right. Ease of study. You can study things,
exactly.
something a little more deeply. Now, earlier you spoke about interaction.
So I'll just throw one other thing in on that. So it's a famous paper from the 1970s by physicists. He won a Nobel Prize in physics, and Phil Anderson. Okay. And the title of the paper is "More is Different." And the idea is that, and it's a very fundamental thing. You can say you have something very simple that has some simple rules, but if you have a lot of those things interacting by those simple rules, that can give rise to sort of complex behavior at a higher level of abstraction that you can't say right away from the simple rules at the base level what is what's going to happen, at a higher level of complexity. Right. So, like we know that humans are made up of cells. We know, how the cells interact, and how, DNA makes proteins and that sort of thing. That doesn't enable us to predict that, humans are going to have complex cultures and, have build giant structures and invent science and all these kinds of things. Right. There's at the next level up, there's very complicated behavior that arises from that simple DNA cells reproducing sort of science, but you can't predict from that what you're going to get a level up. And so that's Anderson's "more is different."
I get it. It sounds like you can only look back and see what that simple cell has accomplished, right? Like now as humans, we've got buildings, we've got computers, we've got all of this. But once upon a time, we were just a single cell. And from there, we've covered a long way and come this far. Yeah. And so it sounds like an eventuality. Of course, you can't predict what the eventuality can be. That's maybe now we can say things are open to speculation because we have the tools to, put things together and recreate the past, or maybe even create a future that we do not know. Like the Hadron Collider was creating something that the claim was everything else came from it. So we've come to a place where we can recreate things. So it sounds like this, that these four fundamental things, although four, this is a number I can count on my fingers, but their permutation combinations are so vast, are like infinite. Now that's another word that is so strange, right? Mathematicians say there are a number of infinities. Like for someone like us, that doesn't make sense. If there is an infinity, that's it. How can there be another infinity if you do not know where one infinity ends? Well, that's the whole definition of infinity, right?
Yeah, that's a branch of mathematics that I will admit I don't understand very well. I've read a few popular treatments of it, but the way that you can show that there's the infinity of real numbers between 0 and 1 is bigger than the infinity of discrete counting numbers. The way that you show that is just mind-blowing, and that those are things that have different sizes, or cardinality is, I think, the term that the mathematicians use. When I say infinite complexity in the context of physics generally means not like literally infinite, in the sense that in the formal sense of mathematics, but just like it's such a huge number that nobody's ever gonna come close to exploring all of it.
Right.
So it's probably technically not infinite, but might as well be.
Yeah, in our lifetime it seems like it. But let's see. And so see this word infinite. So I speak the English language and I see infinite in a certain way. It means a stretch of time or a stretch of things, and that I cannot put a number to. I cannot put a number to it. Mathematicians see it in a certain way. Physicists, see it in a certain way. So this thing about language kind of falling short to convey what it is that we've discovered, and worse still, what it is that we've understood of what we've discovered. Do you feel that language kind of, though it assists, we're talking today, you're telling me things, I'm able to understand, we're interacting, it's the foundation, but it falls short?
Yeah, I think that's necessarily, you know, in a slightly philosophical sense, right? This is fundamentally the problem of, you know, the map is never the territory, right? Or, you know, anything that you can construct, right? Anytime you're talking to another person, what you're conveying is not, you know, the world, but you're conveying a model of the world. Right. And so science is largely about making effective models of the world and some sort of representation that's always going to be imperfect. And, you know, language is a means of communicating those sort of representations. And, you know, that's going to have, you know, layer upon layer of you're making a model of a model and transmitting that to someone else is going to make a model of the model they've received. And, you know, everything gets a little weird from there. So, you know, in technical fields, we can often do a little better than sort of spoken language, because you can write things down in terms of equations and put things in mathematics that takes away one of the layers of ambiguity that frequently come with describing things in words. But a lot of the time, even, you know, the equations we write down are fundamentally a kind of approximation. And so to name drop another famous physicist, famous paper, there's a paper by Eugene Wigner called The Unreasonable Effectiveness of Mathematics in the Physical Sciences. And it's a very famous, where he points out that you know, it seems like the universe that we inhabit is behaving according to very straightforward, simple mathematical laws, but there's no reason why that has to be the case. And so now we've never found a place where that breaks down at all, where mathematics fails to adequately describe some physical process. You know, occasionally we think we do, but then we find, you know, a way around that, and it continues to work. So, you know, everything that we see around us can be described mathematically, but there isn't an obvious a priori reason why that should be the case, right? You could imagine, you know, you could have a totally arbitrary sort of universe. What that would be like to inhabit, nobody really has a good sense of, but it's an interesting problem. Like the fact that that works is kind of amazing.
But I've heard this spoken before, yes, and I know that there is a sort of an answer that people, let's say, who have a spiritual bent of mind and who also have a scientific bent of mind, they kind of bring these two disciplines together and look for the why. Right? Religious texts might not directly hint at physics, but they seem to have a why about the overall creation of everything and how things kind of blend in. But then again, if you think about it, like we are billions of years old, not we, but the planet and the whole creation, every bit of it. Right. So since then, it's taken so long, would it not be right to imagine that we just walk down a thought experiment, that all kinds of chemical reactions were taking place. Finally, there's something happened, which we can now describe in a mathematical equation. And it happened after a long time. So isn't that the why? That it was just reacting, and then more reactions were happening. We might not be the conclude like the end of the experiments, but we've reached a certain point from where these experiments can have benefit from our consciousness. I do not know, but did I make myself clear?
Yeah, so this was like John Wheeler, American physicist, was very into this, and particularly in the context of quantum mechanics, where one picture of quantum mechanics, you talk about consciousness and, you know, like perceiving the universe playing a key role in determining what the actual outcomes of measurements and observations are. And Wheeler was always very fascinated by this idea of sort of the universe observing itself into existence, right? He had this diagram that was like a capital letter U with like the, you know, the Big Bang on one end, and then it, you know, goes down and comes up, and then there's like a, you know, an eyeball on the other end looking back at the Big Bang, and saying that, you know, had this fascination that, you know, we're sort of creating the reality that, and not just our instantaneous reality, but sort of the whole history that leads up to us by making observations. That's a very particular take on, you know, this, and gets in very much into the mystical sort of realm. So it's not, that's not my favorite way of looking at it. I tend toward sort of agnosticism about a lot of these things, in the sense of there are a great many ways of looking at the world that all make identical predictions about what things are going on, and if there isn't a way to usefully distinguish between them, then I don't know that I'm not that excited about debating the finer points of things that can't be in principle distinguished in some sort of experiment.
Okay.
So, I'm an experimental physicist by training, and also just, personality. I'm the sort of person who's like, I want to see it. I want to see it demonstrated in some way. And so a lot of the things that go a little more mystical, I'm like, yeah, well, it could be that, could also be this other thing.
Sure.
Like, if we don't have an experiment that clearly distinguishes the two, I don't know that it's worth
fair enough.
That much argument.
Yeah, fair enough. So personality, your personality is suited for the kind of work that you do, that you chose to dedicate your life to. So now it's always interesting to know what pulls someone towards something. So was it something in you that pulled you towards physics, or you had some question perhaps that you thought physics would be best able to answer?
Yeah, so I'll say I always wanted to be some sort of scientist. So there's a family story about me when I was in kindergarten, visiting my grandmother at her office and where she worked, and somebody there asked me, well, little boy, what are you going to be when you grow up? And expecting me to say fireman or astronaut or something. And I said, well, I'm going to be either a marine biologist or a paleontologist.
Wow.
Two kinds of scientist. And they thought that was hilarious. But I always wanted to be some kind of scientist. Physics, when I took it in high school, and then that I had a very good physics teacher in high school that really got me focused on that and going into college. And I think the thing that I find appealing about physics is sort of that complexity from simplicity thing that I talked about earlier, that it is, we're looking at, in physics, at systems where you can break things down enough to fairly idealized cases that are also physically real. And you can see sort of the effects that we're studying very, very cleanly in a lot of cases. And so, that one of the nice things about physics is, I have a running joke on Twitter, or, something happens in biology, or there's some, psychology result gets overturned, and I'll tweet a link to it with, today in reasons I'm glad I don't work in the life sciences, right? Because there's stuff that goes on in when you're dealing with organisms, right? You have to worry about, are they just having a bad day? Is there something else wrong, or there's some very complicated condition that is off, and so this isn't behaving the way it should because something weird and complicated is going on. Most of the time in physics, right, I don't have to worry about, my thesis research, I studied xenon atoms, right? Xenon atoms don't have bad days, right? They're just, they're atoms. There's no consciousness there. I don't have to worry about, are they in a bad mood? They're not going to lie to my, they're not going to, lie to a poll question because they always want to mess with me. They're very basic things. And so, now, the apparatus that we use to study them and that is hugely complicated and balky and doesn't always work. But, when you get down to interpreting the results of the experiment, I don't have to worry about, there's a whole class of complexity of things that I don't have to worry about at all.
But then, there might be a issue with the semantics in my question now, but what about the uncertainty principle?
Yeah, so the uncertainty principle, right? So this is one of the most famous ideas to sort of escape from quantum physics into the wider consciousness. And so the idea is that there are pairs of quantities in the world that you can't know both of them arbitrarily well. So the classic example is position and velocity. And this is often explained as, you have an electron, you want to know its position very well. Well, you would bounce some light off it, but in doing that, that's going to cause it to start moving, and then you lose some information about how it's moving. Or you if you want to reduce that, then you change the light that you bounce off it, but that loses resolution, so you don't see the position as well. That's kind of a somewhat helpful thought experiment for thinking about it, but it still presumes that there's a definite position and momentum of that electron that you're just failing to reveal through the experiment. Right. And really, it's more fundamental than that. It's that these things, it does not make sense to talk about particles in sort of orthodox quantum mechanics. It does not make sense to talk about an electron having both a well-defined position and a well-defined momentum at the same time. And if you're going to talk about it having one of those things, then you have to throw away everything you know about the other. So that is absolutely true. And some of the experiments I did as a postdoc were sort of probing an application of a different version of the uncertainty principle, and looking at how that shows up in these ultra cold quantum mechanical gases. Right. And so we look at that. It's absolutely 100% real. It's also very, very small. Right. The mathematically, what the statement is that the uncertainty in one quantity multiplied by the uncertainty in the other quantity has to be greater than some minimum value. So it means that neither of them can be zero without making the other one infinite. Right. And that the number that it has to be greater than is very, 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 very small. So quantum uncertainty affects things in a fundamental way if you're dealing with very minute things, but the practical, on sort of a practical everyday scale, it doesn't really do very much. Okay, that's nice. It's not a limit to most of the measurements you would be making. Got it. Yeah, that is what I was looking for. Yeah, that nice way to sum it up. Now, the universe, as you define it, as physics has revealed to you and other physicists like you, it's going from simplicity to complexity, right? So, is it also another way of saying from order to chaos? And if it is so, would you say that when order exists, chaos does not exist, and when chaos exists, order does not exist? Because there seems to be an order even in chaos, right? So yeah, so chaos is a very slippery word, and it ends up having, there is a relatively precise mathematical definition of what chaos is, and that is, I would say, in this relatively precise mathematical description, you can certainly say that kind of thing, or you can say another way. Another word that gets thrown around in this a lot is entropy. Right, is the idea of that the disorder in the universe is increasing. Those both have sort of technical meanings that are, so it's very true to say that the disorder of the universe is always tends to increase, and it's very true to say that the interaction of all these particles and fundamental interactions in physics gives rise to something that you could call chaos in the mathematical sense of, if I know the conditions at this time to this level of precision, I am completely unable to predict what the state of the system will be sometime later. And that's the mathematical definition of chaos. And I think both of those things are absolutely true. This gets into, though, the language sort of problem again, where the sort of common usage of terms like chaos have a lot of baggage, right? It has a lot of idea of, an opposition to the idea of order, or something that's, kind of fundamentally unmaking things in a certain kind of sense. And I would say that that's not really true, that the chaos that we see around us in the universe is in fact very orderly in some respects, in that it obeys all of these mathematical rules, right? There are very strict mathematical rules that govern the interaction between particles, that govern how, space-time is bent by matter and causes gravity, all of these things. Right. The end result ends up looking chaotic in the sense of being extremely hard to predict, but it's not chaotic in the sense of, so the colloquial sense of just it's chaos.
Yeah, like how we
nobody
see.
has any idea what's going to happen. So like
Mm.
there is always order within that.
Right. Right. I understand this chaos, the way you're talking about in terms of complexity.
Mhm.
It's complex. And yeah, I get that sense. So yeah, another thing I'd like to understand from you is what was your we're interested in approaches. How I've already
Mhm.
mentioned that. Like, what was your approach towards physics as a student, and now as an educator, what has been your approach?
So, so I got into the particular field of physics that I'm in because I, as an undergraduate, I got some summer jobs working with lasers in a lab, doing sort of lasers and optics research. And then I heard a talk from visiting scholar Claude Cohen-Tanuji, who later shared the 1997 Nobel Prize in physics. And he was talking about this idea of laser cooling, which is you use the fact that light carries momentum to push atoms around. And if you're clever about how you arrange the light, you can make it so that the pushing atoms around slows them down, right? Causes their motion to decrease. And if you decrease the random motion of a sample of atoms, you've lowered its temperature, right? And so this is just this idea just blew my mind, right? It's the idea that you're going to shine lasers on things and you make them cold as a result. It seems like the absolute opposite of what decades of watching Star Wars movie had taught me to that point. And so so that was just mind-blowing. And it's a very simple and elegant sort of experimental scheme. So, but so I was captivated by that, and that drew me into that particular area of physics. And then I was lucky enough to go to graduate school, and I worked with Bill Phillips at NIST in Gaithersburg, who shared that 1997 Nobel with Cohen-Tanuji. So also for laser cooling. So so there was a really fascinating field to get into and work on that. And so the thing that I like about the particular area of physics is, as I said, like we have a lot of these experiments do remarkably clean demonstrations of bizarre phenomena. So, we can do, atom interferometry, right? We can take a bunch of atoms and sort of shoot them at an experimental apparatus where we arrange for there to be two paths that they can follow through that apparatus, and then look at where they arrive on the far side. And what you see is that they behave like waves, right? Those atoms in a certain sense are taking both paths at the same time, and they're interfering with each other. And the result on the far side is an interference pattern that reflects the wave nature of these atoms, or, even up to complex molecules. And you can do this in a way that you take a picture of it, right? And see, like, there's a bunch of atoms here, there's a bunch of atoms here, there's no atoms in between them. There's other areas where there are no atoms at all. There's an overall pattern that reflects that wave nature in a beautifully dramatic visual fashion that doesn't require a whole lot of interpretation, right? Like, you just look at it and say, yeah, that's a wave pattern. And so those, I think, are the most compelling kinds of physics experiments. So what I do with students is try to get that same sort of thing in. I talk about those sorts of examples. I have some experiments that I do with students in the lab here that go at some of those same kind of things, looking at the behavior of light sources that emit single photons at a time, and looking at the physics of how that same sort of particle wave physics can be, again, remarkably clear and clean in these experiments. And I think that's really fascinating.
So essentially what you're saying, what you felt, and what you're now also sharing with your students is a fascination for seeing things in a way that is different from how they're generally perceived. So that kind of is, I don't know, is it a shock value to it? Is there or is it like, oh, there is something more, I always felt it, and look, what should always be hot is now actually turning out to be cold? Is something like that?
A little of that, and also a little of the kinds of things that we talk about in physics, right? There are some of the underlying rules, like the uncertainty principle, right? This stems from this fact that things behave like particles and waves at the same time. That's very counterintuitive sort of physics. It doesn't seem to fit with our everyday reality, right? But the thing that I find just endlessly fascinating is that, once you have the idea that these particles behave like waves at the same time, you can go and look for that and see it in beautiful, unambiguous ways that really reveal there's this stuff that seems weird and seems counterintuitive that in fact is absolutely undeniably true. And you can show it in ways that are clear and dramatic.
Right.
And so this is one of the, the first book that I wrote is called, we added the word quantum to it a little later. So it's How to Teach Quantum Physics to Your Dog. And the idea of it is, the conceit is it's explaining quantum mechanics through imaginary conversations with my German Shepherd.
Right.
And she latches onto some feature of the theory, poorly understood feature of the theory, and says, well, if I have wave nature, I could go around both sides of a tree and trap a bunny on the other side between me. And then I say, well, no, that's not how that actually works. And there's sort of a silly conversation about that. And then a more serious physics explanation with the dog breaking in. And sort of the great advantage of that approach is it gets you out of thinking about things the way that humans do with our sort of preconceptions about how everyday reality ought to behave, right? What I would always say is, if a bunch of dog treats just materialized out of nowhere in the middle of my kitchen floor, right, I would be freaked out by that. My dog has been waiting for that to happen for years, right? And she's right there on that. And so they're looking at the world with more of a sense of wonder than people are. And so it can be useful to think about these things like from the perspective of a dog. So like approaching the world as like, whoa, hey, like, there's a neat thing. And like, that could be a useful way to get into the subject.
I think so too, because even when you just explain something as simple as, can I go around the tree from both ends and go and trap the, sandwich the bunny and, that'll be my next meal. Visually it creates something light, there is a bit of humor. And then there is an explanation to why it cannot happen. Like, it can't happen, but here's a reason why, which is what physics is giving you. So I found that approach itself, I think it was very, very interesting. Maybe very original.
And one of the nice things about that, we did a relativity book as well. Similar idea, latching onto bits of special and general relativity. The other nice thing about it is because there's some humor in that, it allows you to break things up and get deeper into some things, because you can sort of leaven the spoonful of sugar theory.
Right.
And this is largely, I should credit my first editor, Beth Wareham at Scribner, who suggested that, how about you have like the dog break in every now and then. And so the dog, the explanations are written as if the dog is reading over my shoulder and then interrupts every now and then to say, wait a minute, I didn't understand that. And that does two things. One, it lets me, as we going through the text, it would allow places where there was going to be an obvious question that a human would have. I could have the dog ask that. And so someone who's reading along is saying like, gee, I wonder about this. And then the dog asks that question and I answer it. And that breaks it. But the other thing it does is, like, every now and then I could just have something like really heavy and write about it, and then just have the dog break in and say, like, dude, this is really heavy, and this seems like kind of a lot. And I say, yeah, well, it is, and sort of acknowledge that and just have just a joke at that point, and to sort of break it up enough, and I could slip in the harder material than I otherwise would have been able to get away with.
No, totally. And one thing I keep thinking about, Professor Orzel, and I'm not quite sure if it would be fair to be asking you about this, but I would anyway. I will, and let's see where we go. Since we are talking about these four fundamental forces, right?
Mhm.
Right. So now everything in the universe, known and unknown. Let's leave the unknown out. The known to us,
Yeah, yeah.
yeah, is made up of the interaction of these four forces and their permutations and their combinations. And so, as human beings, we the dog when you're teaching physics to your dog, yes, his central focus is the treat and all of those things. So we can address physics through that. We are limited in the things that we will address because we're talking about a dog, but of course that allows us to bring in the physics in a simple manner. But when it comes to us human beings, us being our central focus, hopefully our desire could be to understand who we are, which means what our emotions are like, what our thoughts are like, how they change, the amount of certainties we have. Is there then a physics to be developed? Because for understanding human emotions and human behavior beyond the statistics and everything, that's what I'd like to know.
So how much physics per se has to say about sort of things on the human scale and consciousness and emotions and that sort of thing is very much an open question. Mm-hmm. And it's hard to say whether there is anything useful to be contributed from physics in that sense. Okay. So this is an area that I approach with a little trepidation, because there is a significant history of older physicists deciding that physics has something really profound to say about human psychology. Mm-hmm. And most of what they come up with is frankly kind of just wacky. Mm-hmm. It doesn't really pan out, and it sort of ends up annoying people who, there's this trope of physicists sort of, parachuting into some field and saying, have you thought about using differential equations to study the thing that you're doing? And, people who have been studying this for years going like, thanks, like that was, that's really helpful. Mm-hmm. So, like how much physics can contribute to understanding of human interactions at sort of a personal conscious level is an open question. I tend to shade toward the cautious side of that, sure. Saying that, like, I don't know that there's all that much that the standard model has to offer to understanding how people feel about interacting with each other. Mm-hmm. Though I will say that a lot of the critical tools that we use for these things mm-hmm. are developed through, processes that start out in physics labs, right? So,
for example,
there are a lot of studies of brain activity that use nuclear magnetic resonance imaging, mm-hmm. and so an MRI comes out of physics, mm-hmm. Or a lot of the sort of microscopy and things that we use to study
internet too, right?
How people are behaving. Yeah, like that mm-hmm. comes from physics.
Mm-hmm.
The tools with which we interact, our conversation is being mediated by fiber optic telecommunication lines, which are transmitting signals as lasers between computers that are powered by semiconductors. That's all physics. So, in a certain sense, we're absolutely indispensable to understanding human interaction. But in a more mathematical sense, probably not that much, because of that whole levels of abstraction problem from earlier.
Right. Because maybe I'm not even trying to look for an answer. Maybe I'm just trying to look for the right question here, right, when I'm talking to you. Because if fundamentally there are four forces, if fundamentally that's the deepest, for the lack of a better word, that physics has been able to take mm-hmm. us, then even human behavior is a part of this, whatever has sprung out from the interactions, right? So that's what I was trying to understand. That I know it's maybe not even a very valid or a logical question, but maybe there is a possibility that since the presence of those four what are they called? Yeah. Those basic interactions.
It's four fundamental interactions, and then there's 12 particles that go with it. Mm-hmm. So it's the combinations of those right. particles interacting via those four interactions. Mm-hmm. I think there is absolutely a sense in which everything around us, everything that we experience, is determined, in a very fundamental way by those forces and interactions. Can we usefully calculate anything starting with those fundamental interactions and getting to human behavior? Probably not. Just because the sheer number of things that you would have to keep track of is so vast that it's just
too complex. Yeah. Then okay, great, this is wonderful. So yeah, during my research, so for research, what do I use? I don't always end up reading papers because they might have an interesting title like that, but then it gets into the formulas, it gets into the physics that kind of is off-putting, because you don't really get the sense of like if it follows a story. In my case, I understand the story, I understand what the ups and downs of a story, the directions of a story, but maybe papers were not my first primary choice. But I go towards films, I go towards videos like by people like yourself, and that gives me a sense of what physics is saying right now about itself. Then so one thing that comes up often is that physics has asked some of the biggest questions. Now, I've also noticed another thing, that with time, even people like us who are watching these videos through TEDx or through podcasts or through, whatever different online format, you also have your own channel. So we tend to kind of take the question on face value. These are the 5, 10, 15 questions that are being asked, and then we focus on the questions. But I think I also kind of step back a little, and I want to understand from you, what do you think big is? What do you mean by big? Physics is asking some of the biggest questions. What is big?
Asking big questions. So I would say, when people say that physics is asking the really big questions, it's like we're probing, everything is at this most fundamental level, these handful of particles and handful of interactions between them, and understanding that absolute most basic level of things. So and that leads to very big questions in the case of particularly like fields like cosmology, where they're asking, what was the universe like 14 billion years ago, right at the instance after the Big Bang, and what will the universe be like in the infinitely distant future, right? That's it doesn't get bigger than that. Where did the universe come from? Where is the universe going? Right? Those are the big questions, and that's usually what people mean by those.
You had listed 2 ends of the spectrum, so to speak, where we come from, where we and where we are going, as 2 of the biggest questions that we can ask, and that physicists have asked, and walk down the road of finding wherever that question leads them. Now, can you also tell me, in between these two, the 2 ends, what are some of the other bigger questions that have been asked? And 2 things from that, how those questions have influenced you in any particular way, if at all? And at what level and to what degree do you think they resonate with everyday people and everyday life?
Yeah, so what I would say is, my career is actually largely between those extremes. I mean, obviously as an inhabitant of the universe, right? I'm between the birth of the Big Bang and the ultimate, whatever the ultimate fate is. But in terms of the physics that I study, I don't really work in a field that probes, like the instance after the Big Bang, or really explores, the ultimate fate of the universe. We're looking at sort of working out the results of relatively low energy quantum phenomena in sort of everyday systems. And there's a sense in which that sounds not as exciting as doing the really fundamental particle physics, or the long-term cosmology, or general relativity kinds of things. But it's actually one of the most interesting and rich areas of physics, because that's where all the practical stuff happens, right? Like, we inhabit a world that is at a relatively narrow range of temperatures, and is in a relatively small region of space, but there's still this vast complexity of all of these particles, and all the forces gives you this sort of infinite variety of stuff. We're never going to run out of things to look at. So the kinds of things that are fascinating in there is as I was talking about earlier, the way that you can do these demonstrations of fundamental quantum properties, I think just endlessly fascinating. There are fields like quantum computing, quantum information, that are looking at, okay, so our universe behaves according to these strange rules where things have both particle and wave character. Can we harness that to do something unique? And it turns out there are certain categories of computational problems that you can very likely solve more efficiently by exploiting these quantum properties of things. So, figuring out sort of certain kinds of complex interacting systems map very naturally onto simpler systems that are themselves quantum and can get you solutions to problems much faster than you could do by a sort of a more brute force ones and zeros classical computer approach. So that's a whole fascinating area. There's a lot that we still don't entirely understand about how physical materials behave. So there's a lot of research in the solid state and condensed matter fields about, how do vast numbers of atoms come together interacting in these simple ways and produce things like superconductor, right? So we have this phenomenon where if you get something cold enough, then the electricity seems to flow through it without resistance. What is the limit to how high can you make a temperature where that happens? And that kind of thing that and these are all fields that have enormous practical applications, right? If we could make superconducting materials that were superconductors at room temperature, then that would solve a lot of problems with energy distribution, right? Some of the technical hurdles of getting power to all of the people in the world who would like to have electrically powered devices. Some of the problems are just, you got to run copper wire and you lose power through the copper wire. And how are we distributing that? A lot of that gets easier if everything just had zero resistance, right? And so, quantum computing, one of the kinds of problems it can potentially solve is something that maps onto this problem of what makes a superconductor. So, you can look at using those quantum tools to solve these intensely practical problems. So I think there's just enormous richness and variety in the kinds of things you can study in this low energy, not at the first instance after the Big Bang, not at the ultimate fate of the universe, but just like how do things work around us is still an enormous challenge.
Yes. And it seems like from what you're saying, although this concept of utopia is, I don't understand it, but, and I know that it's not limited to how we usually see it. Maybe it has many aspects. It seems like physics is trying to create a practical utopia, how we use things if they work well. That in itself is yeah.
I mean, the fundamental goal is, to have a good model of how the universe works that enables you to, from that model, do things, right? To say, okay, I understand how these things interact, and therefore I know that if I take this amount of silicon and add this amount of boron to it, I can make a semiconductor that has these properties. If I, take silicon and add a different element to it, I can make a semiconductor with different properties. I can stick these two together and make transistors, and then boom, we have, computers and the internet.
Right.
Kind of a slow, very complicated boom, but you get the idea.
Sure. And also it sounds like we're, in some sense, we're learning from how things work in nature naturally, and then we try to kind of copy them in the lab and then bring in the human creativity element in terms of its application. What could only work for a orange tree in nature, if we learn the communication, if we learn exactly what's going on there, then we can apply it to many things in human life, right?
Yeah, exactly. I heard my favorite introduction to condensed matter sort of materials physics that I ever heard is from a fellow at Jimmy Williams, I think is the name. I hope I got that right. At Maryland, gave a talk where he pointed out that if you do sort of the dumbest thing you can imagine doing to understand the behavior of electric current flowing through a material, which is say, we're just going to say that there are electrons in there and they don't interact with each other and they just fly through this material as if they're freely moving particles. That works shockingly well. And if like the only thing you have to tweak to make it work really, really well is to say that, the electron has a slightly different mass inside this material, or it has a slightly different charge inside this material. And then it works amazingly well. And there's no obvious reason why that should be the case. And he said, like, a lot of what goes on in that field is taking that realization and saying, hey, naturally occurring materials behave as if the electrons are moving freely inside, just with slightly different properties. Let's see, can we engineer something that pushes those properties to the extreme? Can we make it look like the mass is zero? Can we make it look like the charge is zero, right? Can we push things around inside? How do we do that to make bizarre things happen by taking what occurs in nature and stretching that and using our understanding of how that comes about to make new, entirely new exotic kinds of materials.
Right. So it's just, all of it is amazing, because when I hear you talk, when I hear mathematicians talk, when we had a philosopher of physics earlier, and when I hear you people talk, all of you, the experts, I get a sense that imagination seems to play a strong role in both physics and mathematics, even though in school where, when I was studying, imagination was not, this word was not associated. You take it to your art class, maybe.
Right.
Maybe you take it to your biology class. It's a far maybe. But it seems like there is so much imagination involved. Maybe it's at a certain level, I don't know, that it could actually give us an insight into what imagination is. Right now, I think psychology has the say on what imagination is, if at all, right? But it seems like, because this is imagination at work right there, right?
Yeah, and I think that's to some extent that's a failure of our education systems. Is this idea that math and science are about memorization and sort of applying rote algorithms, right? You learn these are the steps by which you divide two numbers, and you just turn the crank and now for homework here's 50 problems where you just do that thing over and over and over again, and it's just stultifying, right? It's completely boring. And one of the things that we try to do in higher levels of physics education, and now there's a whole physics education research area, people who are trying to find better ways to teach the subject. A lot of it is tapping into this element of ingenuity and imagination that comes from this. It's like, starting more with, okay, we have this problem, right? We want to solve this problem. What do we need to do to solve this problem? We need a technique that will do this thing. Let's invent one, right? And getting that element of, and there can be multiple different approaches sometimes to solving the same problem, right? And getting that element of creativity in from an earlier stage is really important. Right. One of the things that I do, like the school I teach at, Union College, is a small liberal arts college, and so we have a very small number of students, and it's only undergraduates. And one of the powerful things about that is that gives us a lot of opportunity to, first of all, get to know our students and their personalities and strengths and weaknesses and so on, and also to interact with them on, a thing that we do a lot of is research with those students. And it's a really important part of their education, because doing actual physics research is really not at all like doing physics in a class where, we've got a set of techniques. I'm teaching you how to do this technique. I'm giving you problems that will let you practice doing exactly that technique. And we're going to do that. We're going to iterate that through a bunch of things. It's much more open-ended. It's much more, here's a bunch of parts. We're trying to make a thing that will do this. Go to it. Figure out the best way to put those parts together to make this thing. there's an element of play and creativity and ingenuity that goes into that that is largely absent in the in too much classroom instruction. We're getting better at incorporating that in the classroom as well, but it's hard.
But that's good news. It's really good to know that, because that certain amount of involvement, who knows what it could bring out of an individual and out of the experiment that he or she is conducting. So, and
it can make an enormous difference in students' career paths. So there are people who find the classroom side of the more abstract mathematical, prove that this thing is equal to this other thing, right? Find that kind of boring and not that exciting, but are really turned on by, okay, here's the research problem, figure out a way to use these parts to achieve this goal. Really get into that aspect of it and find that really compelling. And so you can bring people into the field who otherwise, might not have.
Right. And if for a student, it also takes away some of the stress, right? Like, it's not being pushed down on the student. The student is fairly willingly involved, right?
Yeah, well, and it replaces it with a different kind of stress. So, what crap, these things are broken, or I put this together the wrong way, or one of my colleagues, Tiku Majumdar at Williams, says one of the hardest things to teach research students is that this isn't a 3-hour lab, right? It's not like you're coming in to do an experimental research program. He said the first day students will work on it for a couple hours, then come see him and say, this isn't working. It's like, I don't know that it's ever going to work. Like, we're trying this. This isn't like your lab associated with the class where I know that this can be done in 3 hours because that's the window that you have to do it and get out of here.
Right.
This might not ever work. We're gonna keep at it for days and weeks,
right,
and see where we get.
I mean, isn't this what you're saying, a proper life lesson in itself? I mean, we do not know how lives are going to pan out, and they are difficult, and it's easy to give up. But if you are trained, physics is training you to look at a certain way. So if you take that insight from physics and you put it back into life, it might as well work, right?
Yeah, and I think pretty much any subject that you get into, right, has its procedures and process and lessons that you can say, and all of it at some level boils down to sort of engaging with the world in a way that I characterize in one of my books as fundamentally scientific. Is that you're looking at the world around you, you're making a model of, okay, how does this work? And then you're testing that model by trying things out and doing different things. And then when you figure it out, then, you share that with other people. Right. And tell them, right, okay, this is what works to solve this problem. And I think that's sort of endlessly applicable to all manner of subjects and life areas.
I think so too. Right. So this is our third series. The second one that we've concluded before this was on language. We spoke to some philosophers of language, linguists, language revivalists. And it was during researching on language that I came across one video. Okay, now it was a very interesting video which showed how a certain cultures in our world look at time differently. So just to get it right, I'd rather read from what the notes I've made. So in Central Andes, there is a language spoken by millions of people. It's called the Aymara. So when they talk about time, the Aymara, this is how they do. They say this is the future facing their back, behind their back, and what they're facing is the past. So it's like you're back walking. That's how they see time. So future,
because you can't see what's in the future.
That's essentially the meaning. Yes. It can really have very subtle, nuanced further interpretations. But that's one way. Then the Yucatec Mayans, they don't have a past. That's a tenseless language. They have a tenseless language, and they don't even have words like before, after, until, while. They don't have those. In English, for instance, somebody had made this comparison. These are studies made over time, and based on statistics, the one researcher is saying that in English, when we have to say later we point to a left, and when we have to say earlier, we point to a right. It might be different, but statistics show that mostly people do this way. Now, this study becomes more prominent and makes more sense when it's compared with Mandarin, because in Mandarin, it doesn't go left or right, it goes up or down. So here, what I'm noticing that in language, which is at our disposal, and our culture gives us, yes, so it has its limitations, but it also has its potentialities, right? But in language, it seems to me, when it comes to this particular subject of time, that we have used time to divide space. Now, later, so we are dividing. There's a lot of, I'm not necessarily saying it's good or bad, I'm just making an observation. I could be wrong, I could be right. But it seems that time has been divided. And or space has been divided using time. There's some kind of a division taking place. But since physics is essentially about simplicity and seeking simplicity in a grand unified theory of things, it's not seeking it's trying to unify things. Can you give us a understanding of what time is as physics sees it?
So there's a couple of ways of thinking about this. The one that I am least comfortable with is, so there's kind of an understanding of time as sort of as a whole that starts at the Big Bang and continues, and then thinking about that in like a really big picture sort of sense, as kind of an entity unto itself. And I don't have a great feel for even like what the consensus of thought is on that. There are people who argue for sort of a block universe picture where the past and the future all exist simultaneously, and you think about that. And there's others that see it as more dynamic and evolving and uncertain. And I just don't have a great feel for those. I tend to be of the opinion that, again, as I've said, I'm an experimentalist by training and inclination. So I tend to think of time as what you measure with a clock, right? So and a clock is a thing that ticks, right? A clock is something that does some regular repeated action, right? The convenient metaphor is a pendulum swinging back and forth, right? And you count how often that thing happens, and that tells you how much time has elapsed, right? And then you're understanding things like that. The interesting thing about that is either of those pictures gets you to a place where there is this linkage between time and space, and there's a very personal nature to time, in that how fast you perceive some clock as ticking depends on how you're moving relative to that clock. And how fast you perceive a clock as ticking depends on where you and the clock are relative to massive objects. So a clock on the surface of the Earth ticks slightly slower than an identical clock placed in orbit, right, around the Earth. That clock will tick a little bit faster because of the effect of gravity and general relativity and so on. So there's this highly individual aspect to it. There's also sort of the fascinating thing that time is necessarily involves repeating cycles, right? You have some process that happens over and over, and we're counting that. So there's this cyclical repeating nature to it, but it's also, in terms of our experience, it's a one-way trip, right? We go from the past into the future, and so that there's a tension there that a lot of the linguistic things that you're talking about are sort of getting at that, right? At this idea of time has this cyclical element to it necessarily, but also has this one-way element. And how do you balance those things off against each other? Right. So you get these very different visual metaphors. Are we going left to right? Are we going up and down? Or is the future behind us or in front of us? And also there are sort of cultures where they think about things in as much more a matter of repeating cycles, right? The famous Mayan calendar is is about these cycles that recur over and over and over. And there's a beautiful poetic description in a book I wrote on timekeeping. There's somebody describing an archaeological find about the Mayan culture, say that that there's a fundamental difference in worldview, that we're looking for projecting things into the future, and reassurances that things are going to get better, and we're looking for progress into the future. Whereas the Maya were looking at these cycles and looking for evidence that things were never going to change, right? Things are always going to stay constant in some sense, that it's always going to come back around. And that's fundamentally a very different worldview.
Certainly. And then you also wonder, like, how does a dog see time? And I think it's all relative when it comes to anything outside of us, because they know it's 1 o'clock, it's time for food. So they'll be waiting.
No, time for food is whatever the earliest time food was ever delivered.
Yeah, even if like we've got 2 dogs, we used to have 3. So we'd feed them, 1 o'clock will be the main meal. So it's a 24-hour cycle. In between treats and all also are regulated, but that main meal time is regulated. So I think it also has to do with how internally we end up adapting. If they are more, they are more, I don't know, closer to something that we've come a little far away from, animals I'm talking about, I don't know. So in just observing them, there's a lot of the things that you can get a better grasp on also. Like for them, that is it. Like,
yeah.
Right? You know what I'm saying? Like, so there's a cycle, food, and then wait for the food, and then food again, and then wait for the food, and then food again. And the click is here also in some sense.
Yeah. There's also like our current dog, who is not the one who's in the talking dog books. Right. We lost her several years ago, but he's a little too smart for us. So like he recognizes things like, I call my parents fairly regularly. I talk to them on the phone. And then, I hang up the phone, and usually I'll call them in the evening. I hang up the phone. And then when I stand up, I'll go, to the back door and let the dog out. So now the dog recognizes if I'm talking on the phone, when he hears the beep of me turning the receiver off, then he runs to the back door, because it's like, no, you beeped the thing. Like now you stand up and you go open the door. Like that's how this works.
Right.
And there's a lot of things that he's picked up on, that he's learned and recognizes
pattern
as
recognition.
Repeated behaviors.
Absolutely.
And it's become something that has to happen.
Exactly. So then time is also, if we see dogs, there is some kind of a pattern recognition. There is some kind of a recognition of a habit. I don't know as humans if we see it that way, but maybe there is a way to look at time like that also. I mean, it's a beautiful subject anyway,
Yeah.
Where it is going, we don't know.
Yeah, it's fun.
Yeah.
So
okay. Maybe I can guess what you would say to this after having spoken to you for a while now, but I'd still like to know, do you think, or before that, can you break down the quantum world for us in simple manner, like the movie Ant-Man did?
Yeah, so quantum mechanics is essentially, I mean, there's various different ways into it, but I would say sort of the fundamental thing about it is this property that things behave in a way that has characteristics that we associate with particles. So you tend to have countable discrete numbers of things, right? But they also have properties that we associate with waves. So they're sort of spread out over space. They're not localized to, not perfectly localized to an individual position. And they interact with each other in ways that produces certain classes of behaviors that we associate with waves, right? If you take 2 rocks and throw them into a pond, you see this pattern of expanding ripples, and then where they overlap with each other, the interesting, complicated things happen, right? And so quantum mechanics is fundamentally about understanding that as it applies to both material particles and to light, and so looking at what effects does that have on the way that things interact with each other and that things behave. So that's fundamentally what it's about. And that dual particle wave sort of nature is what leads to things like the uncertainty principle, right? That we need things to behave both like a particle and like a wave. And the wave nature is more closely associated with the momentum of the particle. So, for it to have a momentum, you need it to have a well-defined wavelength. But something that has a well-defined wavelength is necessarily spread out over space. so it doesn't have a well-defined position.
Mhm.
On the other hand, if you want something that has a well-defined position, you want it to, to be only in one area, that can't really have a wavelength, which means you don't know anything about its momentum. And so that's sort of the how these things come about.
So you would say this is the core of quantum mechanics or the quantum realm, because when you see a film like Ant-Man, right?
Mhm.
Or right? Have you seen that film?
Yeah, it's so any of the
Let's
MCU
not-
kind of things, they throw the word quantum in, and it just means magic. So
I think they have a dialogue in which they have agreed to it themselves. That do you put the
Yeah.
word quantum before everything? And Ant-Man says, yeah, looks like it. But the point I'm trying to say, it seems to me that, see, when we watch it, it seems that the core seems to be that there is a whole world out there which cannot be perceived by your eye.
Mhm.
By your senses, let's see. So that I thought that is the core. That's something so infinitesimally, how do they say, that small, that that's what I thought is the core. But that's the core.
So I would say that there's sort of complementary approaches to getting into this. There's also, there's a sort of an information approach to it that has to, what can you say about things, and what restrictions are there about what you can say about things, and that leads to a lot of the same conclusions. I like the particle wave aspect of it, because I think it gives you both you can understand the microscopic element of it, in that the wavelength associated with material objects is ridiculously tiny. Right. So it's extremely dense. Small.
Mm-hmm.
So it's necessarily, you have to be talking about very small things for these phenomena to manifest in really obvious ways. However, it's also the case that it has profound effects on sort of a macroscopic scale. So to give you an example, right, we're talking via computers, right? The computer chips work by, they're made out of semiconductors, and the essential understanding to making those is knowing that the electrons that pass through the semiconductors behave like waves, and that modifies how they move through the material. And because we understand how that changes the way electrons move through the material, we can exploit features of that to make devices that do digital logic, right? And that enables us, and we can make billions of them in a chip a centimeter on a side, and that's what powers our computers, right? We're also talking via fiber optic telecommunication lines, which are sending our signal back and forth as pulses of laser light. Laser light exists, and you can make a laser because we understand that light has a particle character, and it's emitted by atoms at very particular wavelengths. And so because we have that understanding of the particle nature of light and the way that atoms and light interact, we can make a laser that enables us to make these telecommunication lines work. And so so while quantum physics has this element of the microscopic to it, its effects are most obvious in the world of microscopic particles. It is actually has profound effects on how things in the everyday world behave. In particular, once we've got the ideas of everything behaves like a particle and a wave at the same time, we can work out implications of that enable us to do amazing technological things.
Yes. Okay. Got it. Thank you. Thank you for that. So I have just two more questions left,
Sure.
Professor Orzel. One is something that I like to ask all our guests, like in your case, physics. How would you say, and if at all, physics and your engagement with it over a span of a number of years, decades perhaps, how has that influenced, or has that influenced your worldview in any way?
I think, there's always this question of, chicken and egg, right? Like, did I become a physicist because I think a particular way, or do I think a particular way because I became a physicist? So, it's hard to say, which of those is really the primary thing. I think, and they're sort of self-reinforcing. So it may be a moot point. I think it definitely affects my approach to a lot of things. I tend to take a very empirical approach to many questions about, like what should we do? Like, okay, we're going to think about this in a somewhat systematic and very concrete kind of way. So that definitely affects my worldview. And like I said, that earlier, in response to an earlier question, there are some areas where there are sort of different ways of looking at the same situation that don't produce different results. Then I just don't have a lot of time for that.
Right.
So if I'm sort of looking for questions that can be answered in some empirical, testable way. I want to see an experiment that we could do to answer the question. And if there isn't an experiment that we could do to answer the question, then I'll wait for there to be one before I devote too much energy to it. So.
The last question, have you seen the film 2001, Space Odyssey?
Yes.
Okay, great.
Yeah, it's classic.
Classic, right? And what, according to you, if you have any insight on this, was the monolith?
What is the monolith? So I think the idea in the movie is that this is, sort of, these are it's a creation of aliens that are sort of transcend our normal ideas of time and space. So, they're operating in some, 4-dimensional reality or more than 4-dimensional kind of reality. And that's sort of the gateway for them to interact with our world and for our world to interact with them. And so, but I don't know. Yeah,
okay.
I think it's a connection between, different levels of reality is the idea.
Wow, wonderful. Nice to know that. Yes, that was about all the questions I had prepared for you, Professor Orzel. It was so interesting getting to know your point of view and your approach to physics, and to see that things are changing. And yeah, I think that's something valuable, and we should cherish this change and welcome that change. And yeah, so thank you for coming on.
Yeah, this was a lot of fun. Thank you for inviting me.
My conversation with Professor Orzel showed me how physics helps us probe into the so-called fabric of reality, and how its simple underlying structure grows and becomes a giant mesh of complexity, a complexity or chaos which carries within it a sense of order. It will be wonderful to know your thoughts on the interview and if it inspired your worldview in any way. Thanks for being here. I will see you soon with another interesting mind, demystifying another interesting topic. Until then, take care.